So let's do part 2 of linear algebra, which is a very short topic, short presentation. The topic is big but short presentation. So we work with eigenvalues and eigenvectors. So given matrix A, we have, this is a definition of eigenvector, Ax equal to lambda x. So this is called eigenvalue and x is called eigenvector. Okay, these eigenvalues and eigenvectors have very special properties. So let's see what it is. I mean, all of you know it, but I'm just repeating it here. So a matrix A takes a vector x. So this is a vector x. Okay, and when you apply this on operator A, so Ax will be some other vector. So this is a Ax equal. Okay, so you can call it y equal to Ax. So this could be rotated, stretched. Okay, but we are working with 2D right now. So A will act on as this vector, and it will create a new vector, which most often will not be in the same direction as x or original vector. But there are some vectors, okay, like x naught here. When A acts on x naught, it creates a vector which is in the same direction as x naught. Okay, so x naught and Ax naught are in the same direction. Okay, and this is called eigenvector. Okay, there is another vector Ax1, sorry x1, for which Ax1 in the same direction. For 2D matrices, you can have maximum of 2 eigenvectors. You cannot have 3 eigenvectors. Okay, so the theorem that for n by n matrix, there will be n eigenvalues, but eigenvectors are less than equal to n. Okay, so in the definition of eigenvalue is this: Axi equal to lambda xi. So this is eigenvalue, and xi is the eigenvector corresponding to eigenvalue. Okay, and you may get n of them, but sometimes we get n minus 1. Okay, so we'll use Python functions to get them. We will not compute it by hand or by. I will not tell you the algorithm how to compute it, but anyway, we'll just use Python function. So it's part of, again, linear algebra. So eigen is the function. You can also use eigen h. So h is for Hermitian. Okay, Hermitian or real symmetric matrix are. So this will be cheaper. It will be faster. Eigen h. Please remember, this could be a huge number of matrices, like a big matrix, 1000 by 1000 or even bigger. Eigenvalues. So this one, eigen, I'm going to show you. It gives you both eigenvalues and eigenvectors. But eigenvalues gives you eigenvalue only. So it gives you eigenvalue only. Eigenvalues H will give you eigenvalues for Hermitian matrix. Okay. So we have this function, and there's some more which you can look at the manual. But we deal with only this in this course. So we have matrix 2, 1, and 1, 2. It's a 2 by 2 matrix. So eigenvalues are 1 and 3 for this matrix, and eigenvectors are, okay, the 2 eigenvalues are corresponding eigenvectors, and this is minus 1 by root 2 and 1 by root 2. This corresponds to eigenvalue of 1, and eigenvalue of 3 has 1 by root 2, 1 by root 2. You can check. If you multiply this by vector A, you can just do that. I will not put 1 by root 2, just put minus 1 and 1. What will I get? So minus 2 plus 1 will be minus 1, and minus 1 plus 2 will be 1. Okay, so this is eigenvalue of 1. So 1 by root 2 is normalization. Only which can be set it to. I mean, our normalization means the length of the vector is 1. But here my length of vector is 2. Okay. But it doesn't matter. I mean, Ax equal to b, x equal to x, sorry, x equal to x. You can multiply by lambda x. X can be multiplied by any factor. Okay. Now, geometrically they look like this. Okay. So minus 1, 1 is this vector. Okay. So x is minus 1 and y is 1. And ax naught is same as x naught. Okay. So that's what. But x1, this 1 by root 2, 1 by root 2, this one, it is stretched by 3 times. Okay. Lambda is 3 means this eigenvector is stretched when you apply a on it. It becomes 3 times longer. So that's the illustration. In 3D, okay, of course, we'll get a 3-dimensional space, and we'll have something like this. But by the way, please keep in mind that some eigenvalues could be imaginary or complex. Then it involves rotation and so on. Okay, so these Hermitian matrices, this one is okay to visualize them, but often, of course, you can also visualize those eigenvectors, but it requires a bit of skills. So I will ask you to work with rotation matrix, cos theta, sin theta, minus sin theta, cos theta. Find the eigenvalue of this and see what it does and what are the eigenvalues of this, eigenvalues and eigenvectors. Okay, we can apply this functions to another pretty complex, well, not complex, I mean bigger matrix. Okay, the 3 by 3 matrix. So Ig function, okay, Ig function. It gives you vals and vex, eigenvalues and eigenvectors. Vals are these 3 of them, and eigenvectors are these 3. Okay, so it's a 3D space. Okay, so I cannot discuss any further. This is about it.